last presentation of the day, so hopefully I won't punish you too much and we can get down to the real business of drinking and frolicking and such. So the title of my talk today is going to be After Mirai, Cybersecurity Implications of IoT Botnet Proliferation Against Critical Infrastructure. So a little bit of business at the beginning of this, of course, the infamous disclaimer. Content of this presentation and the statements expressed within it are the opinions of the presenter, and in no way are reflective of any employer or any other entity's view or positions. Content for this presentation is not intended to be construed as original research, but for informational and educational purposes only. So I start off by quoting myself here. Hey, if you're going to quote somebody, why not quote yourself, right? So I said, with IoT proliferation trending towards 25 billion devices by 2020, the threat surface for coordinated attacks to be directed at critical infrastructure targets will grow exponentially, outpacing our ability to effectively detect and respond to cyber threats against them. Just kind of keep this in mind as we go through this presentation and start thinking about what this actually means in the context of critical infrastructure and the things that we use every day, things around like power generation or around part of water pipelines or oil and gas refining, that kind of thing. So the talk, not the talk everyone's thinking about, but the talk that we're sitting in. A little bit about me, kind of the backstory around IoT, and why we even care about it. Of course, there'll be a little bit of primary information, and then we'll kind of dive into Mirai and kind of the impetus of this whole conversation. Some interesting things about it. What's happened since Mirai? So Mirai being kind of the first of its type, what's happened since then? Other IoT botnets, connectedness and convergence. This is something that you'll hear a lot about, and you'll continue to hear a lot about, certainly as we all kind of dive into Industry 4.0 and automation and smart this and smart that. Threats to critical infrastructure and control systems, supply chain implications, countermeasures capabilities. Then we'll kind of bring it all together at the end, and then of course there'll be some time for Q&A and such. Sound fair? Sound good? All right. So a little bit about me. I've been doing this for 27 years, so really long time, hence why I have no hair. I have experience in most of the 16 critical infrastructure sectors, and I actually have expertise in about half of them. And I'm also have expertise in discrete and continuous process manufacturing. What that means is pharmaceuticals, things like food and beverage processing, milling, CNC machines, pretty much anything that you can automate, I've probably done. Die-hard Saints fan, who that? I am the lead global OT security program leader for a Fortune 500 oil and gas full-stream company. I'm a husband. My wife, of course, in the audience here. I'm a father, a research, and a wine manager. As you can imagine, a wine manager means I manage everyone's wine. Everyone's wine, cries, bitches, complaints, moans, etc. So the backstory, just in case you were wondering. So a little bit about IoT and IoT. Probably everyone in this room, unless you've been living under a rock or under a stone, knows what IoT or IoT is. But just for the sake of leveling, we'll give the tech target definition of it. It's one of my favorite definitions. The Internet of Things is a system of interrelated computing devices, mechanical and digital machines, objects, animals, or people that are provided with unique identifiers and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. What? Right? So IoT, or Industrial Internet of Things, is IoT, but we care about machine data, analytics, decision support, and control feedback. And we'll talk about these as we move into why some of the threats and why this is important. But really what we need to know about IoT is that there's some data being collected, that data is being processed somehow, and that data is being moved to something else, to the cloud, to a file share, to a something. That's really all you need to know about IoT for the purposes of this. So Mirai, our good friend Mirai. And why was it such a game changer? So Mirai was the world's first significantly complex IoT botnet. Now, it was not the world's first IoT botnet. You had Linux, Idera, and then you also had, oh God, what was it? I think it was Bashlight, I believe was the other. They were a lot more simple. They weren't nearly as complex. They weren't nearly as distributed as, of course, Mirai is. It was originally targeted consumer devices, so routers, consumer routers and that kind of thing. But now it's so much more. And we'll talk about that a little bit as we continue to go down this journey. It has some very potent variants, to name a few, Satan, Masuta, Pure Masuta, and a few others. The variants were also used in crypto mining, particularly for Monero. Highly adaptable, very difficult to detect, and last but not least, highly prolific, meaning that they can spread really, really quickly and really, really fast. So some interesting things. So we are now up to 7 different variants of Mirai that are active in the wild today, that are attacking various types of devices, various types of components, everything from DVRs to baby monitor cameras. The ecosystem of devices is expanding, and hence the threat surface, right? So the area in which it can attack, and the new processor types are being incorporated as well. So not only are we just targeting very simple devices and simple assets now, but we're targeting the entire processor families with this solution. The actors are getting smarter. Kind of goes without saying, right? Each time a variant is created, so every time we see a variant change, we see some of these exponential jumps in intelligence inside of the variants. And lastly, attacked assets may unwittingly be aware that they are part of Mirai, or for its variants. So it's kind of the zombie hood, right? So they may not even realize that they're part of the ecosystem. So since Mirai, and why is this interesting to critical infrastructure pros like myself and perhaps some of you? So there's a number of other IoT botnets that are out there. And I'm sorry that came across a little small. I was trying to make it bigger and it just didn't work out on the thing. But one of them is going to be Hajime. Another is going to be Reaper. Another is going to be Satori. So let's talk about Hajime for a minute. So after Mirai hit, and it was introduced and it kind of scared the living hell out of everybody, the developers said, you know what, we need to one-up and we need to one-up that ante. So we're going to come in with a Hajime. Now Hajime is not only a botnet, but it is actually a platform in and of itself. And inside of that platform is kind of this modularization. And so each one of these modules can have crypto tools operating. It can have other scripts being running, all types of other things that are deployed as part of the payload itself. Which means that if you infect the machine with this bot or get zombied into this botnet, you're now participating not only as a carrier, but you're also participating potentially in escalating attacks against something else, right? That's some other infrastructure, whether it be just an ordinary endpoint like a laptop, or it could be a piece of critical infrastructure, right? It could be a PLC, it could be a sensor, it could be a gateway, it could be anything. Reaper is a little more interesting again. Highly complex, certainly kind of builds upon, again, what Hajime was able to do. And again, it's still even more modular. And so what we're seeing as an evolution of these IoT botnets is they're becoming more modular, they're becoming more platform capable. With Reaper particularly, it can talk to a number of different platforms, a number of different device classes even, within the same code payload. So when you're trying to monitor for this stuff, or when you're trying to dissect what it is, it actually can talk to different types of hardware, it can talk to different types of systems, and it can subvert and be very stealthy in the process of doing that. Satori is really kind of Mirai with some extras, more or less. It's kind of a little bit of a modification. It is a bit more prolific. It does have a bit more oomph, I suppose. The last one of these is Tori. So it just by a show of hands, how many people have heard of the Tori IoT botnet? Just by a show of hands. Okay. So I had, one in the audience? Okay. So Tori is an evolution beyond the substructure of Mirai. So everything above Tori is a variant of some sort of Mirai, right? It uses some behavioral something that looks like Mirai, and it is derived from it. Tori is a brand new platform. And not only is it a brand new platform, but it in fact can operate on any platform there is. It has the ability to scan and reach into an infected device, figure out what that device can run, what kind of processor it has, what kind of memory capacity it has, what kind of memory it has, and able to formulate on the fly an exploit to actually operate against that platform. Today, we are not seeing Tori being targeted against anything. However, what we believe is that Tori is going to be this next evolution that is really going to give critical infrastructure a nightmare. Because now I'm taking this piece of botnet and I'm going to stick it in an environment that is as heterogeneous as it comes in critical infrastructure. And now I'm getting ready to, potentially release an IoT botnet in there that's going to do all of that heavy lifting for me, as opposed to having to live and persist in an environment for years to try and understand what the ecosystem is. So it's just kind of something to think about. So connectedness and convergence. You'll hear this word time and time again, certainly as we go down our Industry 4.0 journey and this whole notion of converging IT and OT and all this business. Industrial environments have become more connected and more converged. Pretty much goes without saying. The business is interested in knowing what is happening within their processes. If they're doing automation, whether it's discrete or continuous processing, how fast are things being produced? How much money are we spending to produce per unit? How much time are the machines running? And so on and so forth. Things that if you can get really smart about that stuff, then you can save money and cut costs. Increased demand from the business for optimization and visibility. Again, wanting to see what's actually happening in near real time and being able to extract that information in a reasonable fashion. The cloud, and I put the cloud in exclamation or in quotation marks because the cloud can mean a lot of things to a lot of different people, right? We assume that the cloud means that it's something external to us, that's this kind of nebulous thing sitting out there that's taking data and doing something with it. But that cloud could also be internal to an environment, right? It doesn't necessarily have to be out in the ether. Lots of available data to be stolen. And I'm just serious, right? So all of this data is being lifted from these machines. It's being lifted from these assets. It's being lifted from these gateways and being sent into, again, the ether, right? And so it's a lot of data. It's not a lot of data per cycle, but it's certainly, if you have tens of thousands of sensors, that's a lot of data. And it could potentially be a lot of data. And then the standards aren't quite unified. So in IoT particularly, even though many of the protocols have been standardized, the actual applications of those protocols have not been standardized yet. There's a lot of infighting, a lot of different consortia that are trying to drive the standards in their independent direction. But then none of them have come together as one and said, hey, let's just come up with a single standard and let's go with it. They can't do that. It sounds like our Congress almost, right? They just can't get on the same page. Nation state interest. You knew there had to be a slide about this one, right? So if you can imagine, if the malware writers are interested in writing this and they're writing these concepts and they're writing these solutions that are extensible, that can use programming languages and all these other things, it's not just to deny the service of your router, right? They're looking at, some of these malware writers are looking at this as potentially an ability to do force multiplication, right? Or to use it as a distraction to something else. So if I can take some of these very extensible platforms like Reaper, and I can take them and build scripts into Reaper, I can detract from you actually seeing what I'm really after. In critical infrastructure particularly, when the environment is doing a lot of stuff, if you have no specific baseline of what that is, then I can come in there and fly up under the radar, and I could be completely destroying your infrastructure. And you have no idea because you don't know what the baseline is. You don't know what it's supposed to look like. So if I can do that, I can bet you that these four, particularly these bad guys, are more than interested in doing that. And, you know, where we may start seeing this, potentially, if we are not seeing it already, power utilities, water supplies, chemical plants, refineries, things that could be used as a method of terrorism, even. So again, just kind of keep that in mind. So now we're going to get to the threats of critical infrastructure and control systems, individually. So the sensor, the good old sensor. The sensor is kind of the lifeblood. So if you think about most control systems, the workhorse of any control system is a PLC, for the most part. In IoT, that's not true. Because again, I am concerned about lifting data. I'm concerned about extracting data from a machine, a process, taking that data, and then sending it somewhere else. So what is actually capturing the data is the sensor. And that sensor is reading at some sample rate, and it's reading some tag off of your PLC, off your machine, off your fab device, whatever it is, taking that information and shipping it off into the ether. These are also, however, the points of entry for attackers. These sensors can be anything. They can be anything from some sort of embedded, self-contained device with a proprietary OS, all the way up to Raspberry Pis or Arduino devices, Pineapple devices, anything that has limited compute, but has enough compute to take data and send data. That's really the only real requirement. Most of them do not have enough compute to be able to house any kind of significant security stack of any type. There may be kind of some rudimentary things that you can do to the proprietary operating systems that are underneath them, but by and large, they're pretty standard open compute devices for the most part. You can buy some larger Arduino devices, some larger Raspberry Pi devices that can do some of that stuff. But for the most part, people are going with those types of sensors because they're low cost and they're purpose built, purpose designed. So controlled feedback loop threats. So for folks that are not in control systems, not in industrial space, this may be a bit nebulous, so I'll go through it a little slower. So anytime you're building something, you either have an open loop or a closed loop. If it's an open loop, it means it moves from one process to another without a stop. If it's closed loop, it means it completes one loop entirely and it stops, and then it starts something else. That's the difference. Pretty straightforward, right? If I can interact with a control loop, right? If I can change that control loop somehow, if I can augment it somehow, if I can inject bad data into it, if I can augment or change the data that's coming out of it, I can potentially change what the next stage in automation is, right? Many of these sensors that are being deployed as part of decision support, where they're sampling against known parameters, known set points, right? And they're taking that information and they're saying, okay, I need to adjust the speed, rotation, temperature, aperture, whatever there is of this process in order to bring this back within tolerance. If I start altering those numbers, right, if I start changing those things, I am now impacting that control loop, right? So again, it says sensors read data from and sometimes supply data to control loops. So it's not only just reading data and sending it out to the cloud. Sometimes that feedback that comes back from the cloud in enrichment comes back into the sensor and subsequently back into control to change parameters of the control process itself. Bad data, potentially bad control loop, potentially bad consequences. Now, I'm going to caveat that statement. So in many industries, there are still manual fail-safes, right? So for chemicals, for refining, for pharmaceuticals, there are still manual fail-safes that will stop something like this. There are also what they call safety instrumentation systems that will prevent it from going well outside of balance. However, There are also equal numbers of industries that do not necessarily have those fail-safes in them. I won't name any of them because I don't want to scare the hell out of anybody. But there are places where they simply do not have the capacity because the gear that's being used simply does not have the capability to do so. And so in those instances, something like this, when the business is constantly pushing, saying, hey, I need this data, hey, I need this data, I need to get this real-time data, you're going to deliver the real-time data. But there may be some consequences for doing that. The risks to data integrity from external attack or from a malicious insider. So something else to consider here, this doesn't necessarily have to be somebody from the outside. Right? It can be somebody that's sitting that knows the process really well that can inject into it somehow and alter it, or somehow damage it, or somehow damage what is being produced in that process. Supply chain threats. So, any supply chain experts in the room? Just by chance, the show of hands? I kind of figured not, but I just wanted to throw that out there. So interruption to the control loop process from bad data or denial of service against sensors can result in product line disruptions, errors in manufacturing or batching, damaged, defective components, logistics failures, chain disruption or failure. Okay, so let's touch on each one of these quickly. So product line disruption. So for any of you that have ever been in an assembly line or in a factory, you have all these different product lines, right? And each part of it does something different. You have something that stamps the board, something that tests the board, and so on and so forth. If I can impact how those things occur, I can break the line. I break the line, I cause a component to either fail, I cause a component to stamp in the wrong place, I cause that component to catch on fire, I cause that component to fly out of the machine. I can do a number of different things, right? Just depending on what it is I'm impacting. Errors in manufacturing and batching. Where this is a huge deal is in pharmaceuticals, right? If I'm a pharmaceutical company and I have an error in batching, I dump the whole batch, right? Because I don't know where that error went wrong in the batch. And so if you think about something like Levitra, say for instance, Levitra costs roughly about $80 a pill to produce, and every batch is $1,000, or is 1,000 pills. So if I got to dump those batches because I'm getting errant data, that hits my bottom line really, really quickly. And somebody's going to get fired, more than likely. Damages or defective components. This is not uncommon, even in a normal situation where you have a component that gets damaged just because the production line shifts, 2 centimeters to the right or to the left. But if I'm changing this, if I'm impacting it via a feedback loop and I'm changing it, I can make this thing drop a sorter 10 feet away from the board where it's supposed to go if I want to, right? And the only time I'll know that is when someone sees a big pile of metal sitting on the conveyor belt and it's like, well, what the hell is that? Logistics failures. This one is actually kind of interesting because producing product is one thing, shipping it and getting it where it needs to be is quite another, right? And interestingly enough, companies lose more money, not in production, but delivery, of getting things where they need to be on time, under budget, and on schedule. And so if I can impact that, if I can say, hey, I'm sending information back to a sensor that this thing is already left, but it's still sitting in the warehouse, 15 days later, when the customer's calling asking, where the hell is my stuff? And you're like, I shipped it 15 days ago. And they're like, where did you ship it to? You got a problem, right? And in some industries, particularly like oil and gas, there are very specific timelines associated with product being delivered to a site to drill a hole in the ground. And so for every day that driller is sitting there without that part, it's hundreds of thousands of dollars that oil company is having to pay. So guess who's going to have to kick in? That manufacturer that didn't get that part to them, when they needed it. So again, real life implications just by altering something really small and really simple. Then of course, change, disruption, or failure. Again, the entire manufacturing chain causes it to go offline, causes it to fail, so on and so forth. There's a caveat and a good note on here where it says supply chain attacks will continue to become more of a nuisance as connectedness increases in critical infrastructure. So the more we connect, the smarter we get, the more this is going to become a problem. right? And it seems kind of antithetical, right? That, as you would think as you get smarter, this would become less of an issue. But the drive to continue to gather data, to gather more and more information, to get more content, more and more about everything, is also enabling these types of attacks and these types of impacts in these environments. So what we do, countermeasures and capabilities. Asset visibility, pretty easy, right? Can't see it, you can't fight it, right? The key to defending against any threat is visibility. Protection of against IoT, botnets, and critical infrastructure is no different. And really and truly it isn't, right? You're still talking about something that's reaching out to something else through some network means of some sort. It may be using a proprietary protocol, but it's still IP transport for the most part, right? So your traditional types of controls will generally work, generally. And I'll asterisk that, and I'll tell you why that's general here in a moment. It's generally challenging to get accurate asset inventories in IoT devices. So if you imagine you have a plant that covers several acres, right? That's 400 buildings. And I'm looking for a device this big, right? Or I'm looking for hundreds of thousands of devices this big. And not only am I looking for devices this big in that type of facility, but I'm also looking for what they are actually communicating with in a sea of God knows what. Everything from all the automation that's happening in the environment to someone checking their email to somebody checking for a recipe to bake cookies. All of this stuff is all part of the same data ecosystem. So trying to identify something this big in all of that space is a bit of a challenge, as you can imagine. Additionally, some of these devices do not run a traditional operating system. They don't run a Windows or a Linux. They run X. And your tools may not have any idea what X is. May not have a clue. So you see this on the wire and you're like, okay, I know that's not right, but I don't know what it is. And so now you have to try to locate this thing inside of this big plant that's this big. So passive and active methods can be leveraged to understand topography and breadth of threat surface. Now, there's a catch. And there always is, right? There's always a catch. In control system environments, the active part of this is of high debate, right? As to how active you can actually be in those environments and how actively you can interrogate and poll things in order to get information back. In the case of a sensor, when you are polling an active sensor, you will inevitably always force it to miss a checkpoint. Almost always. I have not encountered, I've worked with about 200 different sensors, I have not encountered one that is not true. And when it matters is if it is providing feedback into some sort of control loop or some sort of process. If all I'm doing is just reading machine data and I'm getting that and going to send it somewhere for real-time analytics, that's fine. But the moment I'm using that sensor data to re-inject into some sort of control loop, I can't have any breaks in it because the system is responding, right, based on the information that it's getting. And so if I'm out here actively polling this thing, right, I'm out here running SNMP against it, or I'm out here, running some sort of Nessa scan, I am taking up the limited compute processing cycles that this sensor has in order to produce these checkpoints. So guess what? Now, the system that is getting this data is now doing something different because the data it's getting is different. And so you end up hurting yourself with one of them, their unintentional consequences, right? Unintentional, activity. So you have to be really careful about actively scanning anything in any control system, but certainly when you're dealing with this kind of stuff. Defense in depth. Again, we've all heard this, ad nauseum. IoT devices are relatively low compute. So again, to get back to what we were talking about, how small some of these things can be, right? And they're attached to these machines typically. They may or may not have their own independent network connectivity. They may be wireless, they may not be wireless, they may be GSM, they may be 5G. You have no way of knowing, right? If you're not walking around with some sort of spectrum analyzer, right, you don't know what is necessarily coming off of these devices or where it's sending that data to, unless someone says, hey, there's a device right there with an antenna on it talking to GSM and it's sending data to here, right? Which never happens. I can tell you from experience, I've never had a single user come up to me and tell me that, ever. But when you're designing your defense and def strategies, you have to have some general understanding of where this data is coming from and where it's trying to go. And how sensitive it is, how valuable is it to the people that are trying to get it from point A to point B. If it's just nice to have, it's just okay, if it gets there, great, then you protect it as if it's just okay, and okay, great, to get it there. If it is something that is in decision support, you got to protect it like it belongs to you, right? Because your job and potentially your life really does depend on it, right? Because of the diversity of IoT sensors, a layered security posture is key to managing the threat surface. So again, these devices can be all over your environment, and typically are. And you may not have any way of knowing. If you are responsible for monitoring a refinery, monitoring a chemical plant, these sensors are literally everywhere. And unless you have specifically said, thou shalt not put these on the wire, and thou shalt not send data out of these, they will. Because they'll hook it up and be like, ooh, there's some cool data here. Ooh, I need to cook up another one. Ooh, I wonder if this machine can do it too. And so before long, you have 1,000 sensors sitting on your guest network. And each one of them is sending data to God knows where. So you have to look at things like, you have to have an IoT program and a strategy, right? I know that's high expectations, but you do. You take a gateway and you set all of these sensors behind that gateway so that you now have one place where all this stuff is going. If anything goes awry with that data, you can go to that gateway and say, okay, what's going on here? Right? You can look at the logs, you can have it part of your overall incident response plan, detect and respond. You can't do that if you've got 10,000 sensors going to the internet at one time. Then that. There are not enough people and there are not enough tools on Earth to be able to get through that. Right? So just kind of, as you're deploying these things, and certainly as you're evaluating your own environments for IoT or IoT usage, just kind of think about that you need a choke point, or a couple, at least, as opposed to just having like 20,000 devices going straight to the internet. Not so much. Monitoring. So for this one, oftentimes we'll do a really good job, right? We'll have it all set up, everything will be great, it'll be all pretty in the racks, we'll take pictures of it, we'll take selfies with it, do all of this stuff, right? And then the data goes nowhere. Or the data goes somewhere, but no one knows where it goes, right? No one knows what is actually happening to this data as part of what we care about, right? Because there's two different avenues that we care about. We care about the data itself, certainly. We care about what information is going to what cloud provider and so on and so forth. But we also care about if something is happening in that ecosystem, I need to know, right? If somebody is altering that ecosystem, I need to know. That part oftentimes gets left out, because that aggregation is not always aggregated at a single point. It may be that 20,000 sensors going to the wire. And so now you're talking about taking 20,000 individual sensors and somehow figuring out how to get log data off of something this big in a factory this big. Not going to happen, right? So detecting the denial of service attack requires monitoring the sensors. So in order to see this stuff, you got to be monitoring, right? Because in many cases, these denial of service attacks, because your compute cycles are so low on these devices, it doesn't take much, right? It's not a lot of traffic, so you're not going to see, oh God, the entire internet is raining down on my site. That's not what you're going to see. What you're going to see is these sensors over time trending upward. And they may trend upward a little bit at a time. If it's something like Reaper, it may take a really, really long time because it's really, really slick at user cycle, user cycle, user cycle. Well, that could be the sensor. Right? So if you're analyzing that, that could just be the sensor. That could be its normal behavior. If you have no monitoring, you have no continuous monitoring of it, you don't know what the normal behavior is. So it's just kind of some of those things, again, to continue to think about. Contextual awareness within the monitoring. What's normal? What it? Last part of this, monitoring must trend, providing baseline and anomaly visibility, and be robust enough to support detection and response needs. There's no reason to set up monitoring and all that if you're not going to do anything with it. There's no, that's a complete waste of your time and your money to go do that. So let's bring it all together. We're going to bring it home. Because I know the alcohol is calling everybody. I know it's calling me too. Final words. Mirai was only the beginning of this. So let us not kid ourselves into thinking, oh, that's the worst, that's the bad, that's the worst we can see. That's the worst it's going to ever be. I assure you it isn't. We're just getting started with this. IoT botnets represent a new and highly problematic threat to critical infrastructure as these environments become smarter. So again, as we get smarter in these environments and get more connected, and we spend a whole bunch of time patting ourselves on our backs on how smart we are invertibly also increasing the threat surface and the threats against these environments almost exponentially. As fast as we learn, so do the bad guys. And there's a lot more of them than us, right? We are seeing increasingly complex, powerful, and robust capabilities that require relatively low technical skill to execute. These are not difficult exploits, folks. They're not difficult at all. Many of these exploits are simple exploits that have been around for years. But because I have limited surface on these assets, I have limited capabilities, I have to use stripped down browsers. I have to use, whatever memory registers is available. For somebody that's just a basic script kiddie, that's like the Holy Grail. I don't have to do anything. All I got to do is go download that and run it and walk away, and then lo and behold, I got something. Or lo and behold, I'm now, launching a denial of service attack against Krebs online or something. Nation-state observation of these techniques should have everybody concerned. If we are not concerned, if we're not thinking about whether or not North Korea and Russia and China and Iran, anybody for Iran, right? Who we're picking a fight with at the moment. You think they're not looking at this kind of stuff? Trying to figure out, okay, you know what, I'm gonna stick it to the US. I got something for them. We're not prepared for this. In no form of action. We are not prepared for this type of scale into all of our critical infrastructure. We're not prepared for that. Visibility, defense, and depth monitoring, all necessary to reduce the attack surface created by IoT. It is a concerted effort of all of these different capabilities that is going to give you a fighting chance to be able to help combat some of this stuff. One of these is not sufficient. It's required, but it's not sufficient. And the last thing that I told you I would leave you with, consider how much more smart can we take? How much smarter can we get and actually keep up with it and actually still be defensive? And with that, I hand it back. Any questions? Yes, sir.
My question, I guess, are they buying these from big companies, real names, or is it just, are they going on Amazon?
Okay, so I'm gonna pull my professional hat off for a minute.
Yeah.
Probably about 95% of these components are made in China, ROC, right? We had a particular issue. I mean, if anyone follow any of the Hayway stuff, like with the highway stuff, with the cell phones and all that business. So highway makes components for many cell phones, right? Ones that we sell here in the United States, and we've had some supply chain challenges with highway, right? So the question that you have to ask yourself, and remember I mentioned about that we're not prepared for this, really? This is why. We don't control the supply chain for these cursory parts. And so because we don't control the supply chain for them, we could invariably, as we're on this trek to be the smartest in the room, be setting ourselves up for the most massive denial of service botnet attack on Earth. It's a distinct possibility, right? Because I will tell you that the type of analysis that would need to be done is at the micron level to be able to determine whether or not these sensors have been impacted or have low-level sensor code or anything or embedded code in them that would cause them at some date in the future to spontaneously combust, or at some date in the future to release whatever it is that they're trying to manage, to shut that down, or to speed that up, or to slow it down, or to change it. You have no way of knowing. You have no way of knowing that. So I mean, you bring up an excellent point. And from a practitioner's perspective, we can only do the best we can do, right? It is a mitigated but understood, or it is an understood risk, right? And because it's an understood risk, we cannot quantify or qualify that risk relative to the cost benefit of moving forward. And so companies are not going to sit still because these came out of China, right? They're not. From our perspective, we're thinking, well, the damn supply chain is in China, and it's one of those four that hate us, right? And we're picking fights with them constantly every day around nonsense. So, I don't have a good answer for that, but I can tell you that, yes, it is certainly a primary concern. Yes, sir. Addressing the challenge with the supply chain itself, to the extent that they can, right? So if I buy a sensor, right, it's usually self-contained inside of something else. Very rarely do you buy a raw sensor, right? It's part of some other unit that's linked into something else. So say for instance, you go with like Allied Teledyne, or you go with Siemens even, right? The sensors that they have parts that are from China, even though it may be manufactured in Germany, right? It's still parts. The semiconductor business is really big in Taiwan. It's huge in Taiwan and Singapore and Indonesia, that part of the world. So, I mean, at any point in that supply chain, you could have an impacted component being introduced into these commercial sensors. Absolutely you could. Now, from the standpoint of a Chevron or some of these large companies, whether or not they can actually do anything about it, not really. I mean, there's not a lot of, outside of testing it, and again, you're testing for function, right? You're testing for function of the unit, not an individual component within the unit. So not really. Mm-hmm. Right. Right. And I mean, and again, you could test ad nauseum, right? Most of the times, for any of you guys that do kind of malware analysis or any kind of resilience testing and things like that, that it's only a certain set of conditions that will cause something to behave a certain way. So not only do you have to guess the component, but you have to guess the condition. That could be millions of different permutations, right? So there's only so much safety that you can have when you're doing this. But it's certainly something that you, as a practitioner, need to be aware of and be thinking about. Yes, sir.
So whenever I talk with these like manufacturing, refinery, whatever, so let's talk about their air network and their primary data network, email, whatever somebody's sitting on the web. Is that like something to even pursue anymore, or are we better off accepting that they're going to cross and forcing it all through a single point and just trying to monitor that point?
You're talking about the air. You're talking about the air gapping itself.
To truly force them to air gap these networks, test that it's truly air gapped and somebody did bridge it somewhere, and then only be able to monitor the entry point to the sensor network, the automation network separately from the data network.
I will tell you what you just described is the exact opposite of where businesses are headed, right? So there was a time where these networks weren't connected at all in any capacity, not even to each other. There was a serial cable that plugged into something, and that was it. Once the business realized that you could get data off of this stuff, and this whole Six Sigma and being lean and all this other nonsense came about. Now all of a sudden, we want to get this machine data and we want to squeeze every ounce of productivity we can out of this machine that we just spent $10 million on. And the only way they can do that is by getting data and continuous improvement, continuous monitoring. It's the only way they can do that. Because of that, that data has to be made available to something that is not at the control site on the control network. Right? There's nothing there. There's no one there that cares. Right? They care about, is it running? I put in precursor A. Did product B come out the other side? Right? That's what they're concerned about because it's how to measure. Right? But someone up in the company somewhere is interested in looking at the individual beans and saying, hey, if we move this machine 2 centimeters closer, then we can get 10 more units out of it a day. And so someone is doing that type of analysis, right? And so as long as that's occurring, and now you're starting to see more and more interaction with the cloud. So a lot of this data that is coming out of these environments is being sent up into clouds like Vimana or in the Smart Shop and some of these other entities, and it's being permuted and transformed and enriched, mobilized, and taking that data and then sending that data back down into the control environments, either for introduction into control itself or to a control engineer or a process engineer or an operator to be able to take that data and make some sort of change and adjustment for optimization purposes. So in some places, air gapping actually works as long as you don't need the data from it. Right? If the only thing you need to do is operate, you can air gap until your time.
I guess my question is like, is it still useful if you're saying you control everything through a single point entry, like create a gateway? Am I still better off being like, no, keep the air gap, we'll put another internet gateway on your control side, and that way I only need to monitor that for like sensor data leakage?
You can, you certainly can. So keep in mind that this sensor data looks a lot more like IT data than it does manufacturing data. So you're not going to see Modbus sitting in it. You're not going to see Profibus. You're not going to see any of that kind of stuff. It's going to be primarily coordinate. So it's going to be a string this long, and it's going to be numbers with commas, right? And then something's going to ingest that, right? I mean, that's what you're going to see. You're going to see a string of data about yay long, and numbers and coordinates and all this business. And that's going to mean something to something. Right? It's going to mean something to some form of analytic that's sitting in the cloud normally. That's taking that machine data that it's getting and actually formulating business value. Some sort of business optics into what that machine is actually doing. So from the standpoint of whether you continue to air gap, it's really more of a business decision about whether they continue to do that. And certain industries, it's kind of their standard as to how they operate and how they function. But invariably, very few environments stay that way, right? Because at some point, someone's going to go plug something in because they're going to need something off of one of these machines, even from an operational perspective, right? They're going to take their laptop and they're going to walk in there, they're going to plug it in behind a data diode, they're going to plug it in behind something, and that machine is going to still be sitting on the corporate network on wireless somewhere. So this notion of a perfect air gap, I'd be really suspect of that whenever people say it. There are attempts, right, to do it. Is there value to keep the data separate? It's really more of an individual design decision based on just like in the industry that you're working with. In some industries you have to, right? In some industries you have to keep certain types of data away from other types of data. So if it's regulated that way, you got it. Did I answer your question?
Yeah.
Okay. Yes, sir.
How effective is regulation?
So in order to have regulation, you have to have standards, right? You have to have a unified standard of some sort to base that regulation off of. So I'm gonna put one toe on my soapbox for a minute. Our Congress can't do like basic things, right? So you're telling me you want our Congress here in the United States to come up with legislation to dictate what IoT looks like? Do you really want them to do that? I mean, honestly. I mean, do you really want them to go down that path? If I'm a company and I'm selling said unit at 15 cents a unit, the last thing I'm about to do is stack some damn regulation on top of that. Because now I'm going to have to sell this thing at $1 a unit to deal with the overhead. Not happening. You know, that whole self-regulation thing, not so much. You know, but, you know, so Congress supposedly is trying, right? I've seen some evidence that they're trying to wrap some sanity around kind of our cyber posture and all this other stuff. But again, in the lack of a unified standard, no, I don't see it. And again, with the Congress that we got, no. Now I'm gonna take my toe off this soapbox. Anything else? Yes, sir. Oh yeah.
We worry about that now.
Oh, the privacy problems, yeah. Well, so the average consumer, right, has no concept of the fact that a generator sitting in a power plant has thousands of sensors on it, and it's sending thousands of elements of data to something that is in the ether. And regular folk don't know anything about that. Nor do they care. All they know is I walk in my house and I turn the lights on, they come on. Or I go to the water spigot and turn the water on, it comes on. That's it. You know, they have no concept of what all that other stuff is back there. And so, but they do know what a Fitbit is, right? You know, they do know what an iPad is or an iPhone, right? You know, all of these are IoT devices, right? All of them. The wearables, any wearable, anything that's tracking your heart rate. These are all IoT devices. But they care about that. Well, you can't have my Fitbit data. But they're not so concerned about, you know, the sensor data coming off their power generation. You know, and I'm not sure I would be either if I weren't in the industry. I'd care less. Anything else? Thank you very much.